Hi, in this part of the lecture, I'm going to talk about the actual VCR cycle. An actual VCR cycle differs from the ideal one in several ways, mostly due to the irreversibilities occurring in various equipment. Two common sources of irreversibilities are fluid friction, which causes pressure drop, and heat transfer to or from the surroundings. As seen in the TS diagram of an actual VCR, several irreversibilities can be noticed in many process steps. First of all, the fluid friction in the pipelines connecting between various equipment causes pressure drop and also heat transfer to or from the surrounding. They are line 2, 3, 4, 5, 6, 7, and 8, 1. The temperatures in line 2, 3, and 4, 5 are above ambient temperature. Therefore, some heat loss to the surrounding could take place. Okay, suppose that this is the ambient temperature level. Okay. On the other hand, the temperatures in line 6, 7 and 8, 1 are below ambient. Hence, there will be some heat transfer from the surrounding. The pressure drop in line 2, 3 will result in more work required in the compressor to compensate for this line pressure drop. Okay, you can see that we have a pressure drop in line 2, 3 here. You have to compress to a higher pressure to compensate for the pressure drop in this line. While the heat loss in line 2, 3 will give benefit in terms of reduced condenser load. The pressure drop and heat loss in line 4, 5 will give benefit in terms of increased refrigeration capacity. Okay, when the liquid become more subcool, okay, it will flash through the valve and you have more liquid. You have more refrigeration capacity in the refrigerator. The heat transfer in line 6, 7 will reduce the refrigeration capacity. Okay, you can see that if you have a pressure drop from 6 to 7, okay, you can see that this part will be the reduced refrigeration capacity. In the actual refrigeration system, line 6, 7 here, okay, is normally short. The effect of irreversibility in line 6, 7 is therefore insignificant. Okay, very small, this part. And lastly, the pressure drop and heat transfer from the surrounding in line 8, 1 will bring the fluid further into the superheated region. Hence, it will increase the specific volume of the vapor. The power requirement to the compressor is therefore increased, since the steady flow work is proportional to the specific volume. Line 8-1 is normally long in the actual system. Okay, the pipeline connecting between the evaporator and the compressor, which is outside the room or outside the cold space, is normally very long. So the irreversibility effect in this line is therefore significant and cannot be neglected. With the frictional effect and heat transfer, the compressor can become a reversible compressor. if the frictional effect dominates during the compression process will follow part 1 2 with an increase in entropy. So you have positive delta S, okay, increase in entropy 1 2. On the other hand, if the heat transfer to the surroundings dominate the process, the compression process will follow part 1 2 prime instead. So in this case, you can see that in part 1 2 prime, you have decrease in entropy with the heat transfer effect. Okay, we have cooling effect. Cooling effect here during compression. Okay, during compression. This condition is more desirable than the isentropic process, since the specific volume and the work requirement will be smaller in this case. Therefore, the refrigerant should be cooled during the compression process whenever it is practical and economical to do so. We could also have pressure drop in the condenser and the evaporator as well. It is not easy to operate the condenser and the evaporator precisely to achieve sat liquid at the condenser outlet and sat vapor at the evaporator outlet. Therefore, the liquid from the condenser is slightly subcooled. Okay, number 4 is slightly subcooled. Okay, this will do no harm in the tottering process. Okay, we will have bad effect in the tottering process. The vapor from the evaporator is slightly superheated to ensure dry compression in the compressor. Number 8 is slightly superheated. Okay, to ensure dry compression in the compressor. However, the degree of superheat should not be so high, since it will increase the power requirement in the compressor here. So you can see that with all possible irreversibility in the system, you can see that the shape of the refrigeration cycle would be a lot different from what we have seen in the ideal VCR before. Okay, so the calculations of the actual VCR will be a lot more complex than the ideal VCR. Now let's have a look at the example of actual VCR here. We have a refrigeration system using refrigerant R14A as the working fluid. The refrigerant enters the compressor of a refrigerator as superheated vapor at 0.14 megapascal and minus 10 degrees Celsius. Sorry. This one. So this is point number 1. Okay, this is a little bit superheated at a rate of 0.05 kilogram per second. So this is m dot. Okay, and it leaves the compressor at 0.8 megapascal and 50 degrees Celsius. So this is point number 2. Okay, after compression. Okay, so you can see from the TS diagram as well, the condition at number 2 is also fully defined. Number 1 is fully defined. The refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 megapascal. This is condition at number 3. You know both temperature and pressure. Number 3 is also fully defined as well. And then it will be throttle through a valve to the pressure of 0.15 megapascal. Okay, this is point number 4. You know the pressure at point number 4. Okay, if we ignore any heat transfer and pressure drops in the connecting lines between the components, okay, we want to determine the rate of heat removal from the refrigerator space. So this one is QL dot. We want to determine QL dot. And the power input to the compressor, which is W dot in. Okay. We also want to determine the isentropic efficiency of the compressor as well. Neta compressor. And lastly, we want to determine the COP of this actual refrigerator. Okay. Now let's have a look at the property that we already have. Okay, I can just summarize all property that we have in this table. Okay, you have 4 states. Okay, 4 thermodynamic states. State 1, 2, 3, and 4. At state 1, 2, and 3, you already know the pressure and temperature. So state 1, 2, and 3 are fully defined. You can consult the property table, okay, to get the remaining property that you want to know. Okay, for example, at state 1, you can check from the pressure and temperature values, and you find out that it's a superheated vapor. Okay, so you can go to the superheated table of R134A, and you get the value of enthalpy of 246.36 and entropy of 0.9724. Okay, so this is the property that we obtained from state 1. At state 2, when you check the pressure and temperature, you find out that it's also superheated vapor as well. So you can go to the superheated table and obtain the enthalpy value at this state. Now, at state number 3, when you check the pressure and temperature, you find out that it's a subcooled liquid. But unfortunately, you don't have the subcooled liquid table at 0.72 megapascal. So you have to make some approximation in order to determine the enthalpy at this condition. Okay. Now the enthalpy at this condition can be determined from here. You can see that at the subcooled liquid region, okay, the point of the subcooled liquid is very close to the sat liquid line. Actually, point number 3 is very close to the sat liquid line. So both properties, whether it would be enthalpy or entropy, can be approximate by using the enthalpy and entropy of the sat liquid at the same temperatures. Okay, so enthalpy H3 can be approximate from enthalpy of sat liquid at temperature T3. Entropy here of subcooled liquid can be approximate from entropy of sat liquid at temperature T3 as well. So this is a good enough approximation because the region between the subcooled liquid line and the saturation liquid line is very close to each other. This approximation is good enough. Okay, so you can just determine the enthalpy of this subcooled liquid by using the saturated table. Okay, you can take the enthalpy value of the sat liquid at 26 degrees Celsius here. Okay, and that would be 87.83 kilojoule per kilogram. Okay, and lastly, at step number 4, you know only the pressure value, but you know that as a result of the Joule-Thomson expansion, you will have the same enthalpy value. So you already have H4 equal to H3. Okay, and you can check that number 4 is in the two-phase region or in the mixed phase. Okay, so basically from this summary table, you already have all enthalpy values, so you can do the energy balance in each process step to determine the energy flow, whether it would be the work or whether it would be the heat flow easily. Now for the first question, we want to determine QL dot. Okay, so for QL dot on heat removal from the refrigerator space, you can just do the energy balance in the evaporator. So QL dot would be M dot multiplied by H1 minus H4. You knew all the value. So substituting all of them, you get QL dot of 7.93 kilowatt here. You also want to determine the power input to the compressor. It can be calculated from the energy balance in the process 1-2. So that would be M dot multiplied by H2 minus H1. So power requirement would be 2.02 kilowatt here. The next question is, we want to determine the isentropic efficiency of the compressor. Isentropic efficiency of compressor is defined as the isentropic work divided by actual work. Okay, it would be H2S minus H1 divided by H2 minus H1. Now from the table that we have in the previous slide, you already have H1 and you already have H2. You need to know the enthalpy at the compressor exit when it was isentropic or H2S. So to determine H2S, you know the pressure value 0.8 megapascal. You know the entropy value S2S equal to S1 equal to 0.9724 kilojoule per kilogram Kelvin. So you can take these two pieces of information to calculate the enthalpy at 2S by interpolating from the superheated table. So you get H2S at 284.21 kilojoule per kilogram. Now you can substitute H2S back into the isentropic efficiency equation. So you get the isentropic efficiency at 93.9%. And lastly, the COP of the refrigerator can be calculated from just what we get divided by what we give. What we get would be in terms of the cooling effect that we obtain divided by what we give, which is the work input required. So COP of this actual cycle would be about 3.93. Okay, and that would be the answer for the last questions. That should be all for this example. Okay, see you next time in the part 4 of this lecture. Goodbye.